Okay, today's topic is the DC motor control system. Now as in the last videos, I already given you the DC motor control. So while you not system speed control and the timely braking, so then I already given. Now that today we will utilize the SCR speed control system. We use the silicon control rectifier. So this is what electronic soft step control to control the AC motor and the DC motor. So this is we use as a SCR. So silicon control. Rectifier. So silicon control rectifiers are utilized to control the AC motor and the DC motor. So this is the AC motor speed control they are utilized. As well as the DC motor speed control. So AC motor speed control and the DC motor speed control system we use as our SCR system. So input can be either a single phase or three phase. So single phase system we use the one four ways rectifier bridge. On the three phase system we use a three phase bridge rectifier bridge. So why we use the SCR control system is this is for the SCR here. The input current will be this current. So here we provide a gate control. Depending on the gate firing angle, output current depending on. So this one is the output waveform like this. So this one, this angle. This magnitude is a conduction. So the shaded portion in conduction is depending on the firing angle alpha. Alpha means the firing angle. Depending on the firing angle, so output conduction is changing. So this is we use for the SCR for the AC motor speed control system. So then we also utilize for the SCR in the converter system. So this is a three-phase system. So this is three-phase. So three-phase we use the SCR. So SCR we use as a three-phase bridge system. So three phases bridge system we also utilize SCR. So SCR we use and this one we connect it to the load. So in this case we have to connect the three phase. So this is for the three phase circuit. So we use the SCR. This is the SCR system. SCR system we control the three-phase system. So by controlling the three-phase, the output input body will be like this. This is the input phase A, phase B, and the phase C. So this is the input body. So output is we can call this most repair, lower repair output body. So this is the output. So output DC. So those are the output DCs acquired by using the SCR system. So this output DC is supplied to the silicon control rectifier system. So we use the SCR drive motor. So block diagram SCR control motor. So SCR control motor, so then we use AC input. It's feed to the SCR unit. So SCR unit this is the output voltage V0 is fed to the motor. So motor is running, so this is the motor produce the speed. So this speed is a sense by the sensor. So sensor speed and this will bring the speed output. So this sensor is made as a combination. The signal, you make a combination, it's compared with the reference. And then the chain on the speaker we fed to the grading circuit. So this grading circuit we fed to the SCR unit. So this is for the SCR control some motor. So AC input usually change to the DC, and this DC this voltage is depending on the firing angle determine the amount of the voltage. So depending on the voltage the motor speed will be changing. So this will be sensed by the sensor, the tachometer, and the reference signal make the comparison, and the gating circuits are provided control function to the SCR unit. So this is for the SCR control. So the point we have provided these circuits if DC is not pure DC, it can provide a repair. So those repairs are no good for the DC. Because of the repair, it can create a heating, harmony, and also the vibration. So these repairs are not only delay the machine, but also delay the insulation. So this is the repair happen. This for us block diagram SCR control system. So DC motor we can control by the silicon control rectifier. So SCR we utilize to control the DC motor or AC motor. So we adjust this gauge the fire and gauge. We can regulate the voltage. So by changing the voltage, we can change the speed. So this is for the SCR. So in this case, in industry, we use a single phase or three phase. So this is for the three phase. Input three phase AC supply, and we change to DC. So DC output will be like this. So this is DC. So this is our repair output. So this one is not constant because the data we use this waveform. So those are we can. This is we call it repair. So those repairs create a heating effect. So heating effects will produce. So repair can produce a heating, harmony, and vibration. So the repairs delay the machine, delay the insulation. So those repairs are produced by the high frequency switching PGBN device. So start with a modulated device system. Start with modulated device system means the switching rate. AC waveform is formed by the switching rate. So those switching rates determine the AC waveform. So this is the bandwidth modulated system. So bandwidth modulated system produces a repair. So we need to filter and repair by the filter. So this is the typical control system for the DC motor system. AC input, we use the SCR unit, so we change the output. So the DC motor we change the speed, and the speed is sensed by the sensor, and we compare with the repair and the gating circuit, we feedback to the SCR unit. So by the filter motor speed is regulated. And the motor speeds are related to the equation, so that we can plot the diagram for the horizontal is the top, for vertical line is the top, and the horizontal line is the speed. So top we can calculate T equation is equal to the KT phi PT divided by RA. So this is for the top equation. So in this case, we also calculate the KD. KD constant is a formula we can find. So this is the KT is phi square by RA. So this is for the so in this case, this line says that this is T function. T function is equal you see the gradient. So this gradient can be calculated. The formula will be KE KT phi square divided by RA. So this is the gradient of the line. So that we can need to calculate the KE, KT, and the phi square into RA. That's the equation. So that we need to find which one is the KE and the KT. Phi is the plus, V is the terminal voltage, RA is the armature resistance, T is the torque. So we have to calculate the KE and KT. So KE, KT need to be calculated. So here is T is the plus torque. The phi is the plus, and I is the armature current. Also, we can calculate the KT. KT is equal to P Z divided by 2 pi A. So P is the number of poles, and Z is the number of armature conductor, A is the number of armature per bar. So create a number of poles. Set a armature conductor. And just a easy armature pedal part. So this is what about PZ divided by 2 by A. So in this case, we also need to calculate the KE, so by this formula, and also KE we can also calculate by formula. This is the PZ by 60A. So by this way, we can calculate the KE and the KT. So then, we also need to calculate the EG. Generator volume EG is equal to the KE phi into N. So here N is the speed. The speed of the motor we can calculate by this equation. So EG is the generator voltage or the fact E and F. So the torque equation, generalized equation for the torque is this week's formula. This is the KT into phi into VD by RA minus KE, KT, phi square and divided by RA. So this is the expression of the torque. The torque and the speed relationships are diagrams we can calculate. So this is the equation. So depending on the kind of motor, so sometimes our motor will be the cap like this. This is for the torque. It's a particle line and the speed is a particle line. So we use the torque equation we can draw like this way. So this is a 4-pole one armature operating in the P of plus 0.01 waiver. It's a one with the 360 armature conductor. So we need to determine the expression of torque as a function of the P, the VD 250 volt and the RA 0.10. So this is the equation. Okay, so this is that normally we have to write the expression of torque equation. Torque equation is we use a generalized equation here. We use a thing. So KT into phi VD divided by RA minus KE KT phi square N divided by RA. So this is the equation generalized expression of the torque equation. So the two, this is that torque is a function of the speed. So to write this equation, we need to determine the KT, we need to determine the KE, we need to determine the torque. So they have to calculate. So the first we calculate the KT. The KT formula is already given here. So this is the CSS we can calculate is equal to the PZ divided by 2 by 8. So this becomes 4 into 360. So divided by the 2 into 3.1416 into the A. A is equal to the 2 multiplied N. So 2 multiplied 1. So for the whole one is a 2 multiplied N. So this is the 2. So by solve this is a 114.5. And also the KE. So PZ by 68. So this is the 4. Say the 360 and 60 multiplied 2. So you got the 12. So now you substitute the formula. So KT is already here is a 114.5 and the flat is a 0.01 and VD 250 volt resistor I 0.1 minus this is the KE is a 12 multiply 114.5 multiply the plus square is 0.01 square into N divided by 0.1. So that will be the 2860 minus 1.38N. So this is for the principle of the DC motor speed control system. Okay, so now we could calculate the duty cycle calculation. This is a new topic. So duty cycle calculation means when we are running the DC motor is we use as a speed control. So this is we use for the SCR control system. SCR control system is an electronic control system. The electronic control system, so that we are supplying the motor with the path with a modulated waveform, PWM waveform. So those PWM waveforms are applied to the motor. Because of the switching rate, the waveforms are being applied to the motor, so we have to calculate the RMS value of the switching rate. So this is important because the only RMS value is really the rotated motor. So then now I give you the duty cycle calculation of the pathway modulated waveform. So this is ways that we have to calculate the RMS value of the switching rate waveform. To calculate the duty cycle and the RMS value. So the as well as the selecting the motor, then is capable of developing the sufficient torque. According to the motor equations, we can calculate the torque equation. So this torque and the speed equation we can calculate. So that this is depend on the motor flux and also the number of goes down, the armature parapath, it can produce the appropriate torque. So this torque we can calculate. So not only the motors are capable of carrying the load, they also need to withstand the heating effect. So as well as the selecting the motor, this is the capability of the developing the sufficient torque to drive the load as the required speed. The motor so chosen must be able to provide this torque and not suffer any undue damage as a consequence to the heat produced within the machine by the current in the various winding. So the motor got the armature winding, P windings. So those are inside the P winding when the current is flowing, it will produce a heating effect. So this heating effect need to be withstood by the motor. So that the heating effect is the function of the RMS. So therefore the RMS value the load must be the optic. So this is why we need to calculate the duty cycle calculation. Okay, so firstly we calculate for the RMS value for this waveform. So this waveform is given here. So the final value is 2. So originally we start from the 1, 3, 5, 7, 9, and the 10. So this is originally the 8 is it. So this is the equation is given at y0/28. This is find the RMS. So this one RMS values equation is the formula. RMS value is square root of 1 by y integration 0 to y square dA. So this is the equation to calculate. So then 1 by y means how many total division. Total division is 10 division. So total 10 division, and then so this is for the y square. So this is the you have to indicate to the 1 to y. So this is the y is the number of division. Y is the 10 division. So 10 division you have to substitute to the 0 to 10 you have to integrate. So that we calculate RMS. So in this case y value is given a 10 division. Here you see how many 1, 2, 3, 4, 5. So this is a 10 division. 10 division means 1 by 10, integration 0 to 10. Y square, so y square dA, y is only given as 0 by 2, 8. So 0 by 2, so 8 square into dA. So this is the equation we substitute. Okay, so this one we substitute, so then we use this calculation, so then we use 1 by 10, so 0 by 2, 8 square is we use 0 to 10, 0 by 0, 4, 8 square dA. So this is the square root of 1 by 10 multiplied 0 by 0, 4. So integration 0 to 10, 8 square dA. So 8 square dA is you make the integration. So this is 1 by 10 multiplied 0.04. So this is the 8 power 2 by 3. So integration from 0 to 10. So that you substitute the 10 in the place of the 8. So that way is 1 by 10 multiplied 0.04 multiplied 10 power 2 divided by 3. So then you got the RMS value is 1.153. RMS value you can calculate by this way. We had to calculate the RMS value of this waveform. So this is the A portion and B portion. So we have to use the graph, the table. So this is the section. So this is duration. and the value and area. So this is we can utilize in this table. So the for the section A, the duration is a step from 2 to 5. So 2 to 5 means you have to find a duration. So this is 5 minus 2 is equal to 3. So there will be the 3 seconds. The 3 seconds in this case are value with the 2. So area makes a formula with the duration multiplied value. Duration multiplied value. So the duration is we utilize the 3, value is 2, so this is we call it 6. So this is for the A. And then B, section B. So section B is start from the 7 to 9. So 7 to 9 means this is you have to value duration. 9 minus 7 is equal to 2. So there will be the 2 seconds. 2 seconds of value will be the 4. So the duration multiplied value is the 4 multiplied 2 is equal to 8. Then you have to find the total. So total is 6 plus 8 that will be 14. And then we have to find the average. So average means total area divided by total duration is the average. So this is the total area divided by total duration. So the total area is 14. Total duration is CR start from 2 and add at the 10. So total duration is 10. So that will be the 1 by 4. So the average value is 1 by 4. So the RMS value is square root of average. So this is the square root of 1 by 4. So the RMS value is 1.183. So that kind of duty cycle, the RMS value is 1.183. So this means that when we are running the motor, not all the time motors are running. Sometimes motor is running, taking the load. Sometimes the motor does not take the load. So in this case, taking the load and release does not take the load. Those are cycles. So those cycles are influence the motor. So that we have to calculate the effective and the RMS value of the overall load by using the second of method. So you have to calculate the RMS value. Then so there's a loading effect calculated, then the equals is related to the heating effect. So then you can calculate the motor heating. When the motors are you drive the motor to the connected to the supply, so usually the motor has to overcome. So motor has to overcome the supply inertia. So to the static inertia. At the time the motor